Right, in 86, we're given these three functions, and they're already differentiated twice. We have f double prime, g double prime, and h double prime of x. So we're given their second derivatives, and we have to figure out which of these, it could be more than one, has exactly 2 points of inflection. Okay, so let's recall that inflection points are when the graph changes from like concave up to concave down, or you could say concave down to concave up. So in other words, the second derivative goes from being positive to negative, or from being negative to positive. Second derivative, that is. So we want to first start to look for possible points of inflection. So possible points of inflection would be where the second derivative is zero. Well, the zeros of the second derivative. Then once we find the zeros, we look to see if the sign of the second derivative changes. Because it's possible to have a zero, like for example, you could have a graph like this. You could have a zero here, but the graph is still, positive on both sides. So there won't be a point of inflection, even though the second derivative is zero there. So it's just a possible point of inflection, that is what it's saying. Anyways, so I graphed these on Desmos instead of my graphing calculator. My graphing calculator is having an issue. So let's switch to the screen here so we can see what these three graphs look like. So let's new share. Okay, so here you can see the three graphs of F, G, and H. F is in red, G is in blue, and H is in green. So you can see that F of X has a zero at -2, and has a zero at 0, and has a zero at 1. So here's a point of inflection because it changes from positive to negative at -2, positive to negative. And it's negative all the way up to here. Then at 0, it's also a point of inflection because it becomes positive there. But at 1, it's not a point of inflection because it stays positive after and before 1. So there's only 2 points of inflection for F, at -2 and at 0. And same thing for G. There's 2 points of inflection for G at right here about. It goes from positive to negative, then to positive again. But see, it never becomes the blue graph never crosses the x-axis again. It only crosses it twice. So the red graph crosses the x-axis twice. Those are 2 points of inflection. So F and G have 2 points of inflection. But H has 1 here, 2 here, 3, 4 has 4 points of inflection. You can see the cross of the x-axis 4 times. So the answer would be that F and G have 2 points of inflection. So let's switch back. And our answer would then be C, F and G only. Or 87. The table above here gives values of F at such values of X. If F is a twice differentiable function on the interval 1 to 5, which of the following statements could be true. Okay, so let's look at what's going on with F of X. So it's going from 9 to 4, so it's going down by negative, so it's decreasing by 5, then decreasing by 4, then by 3, and then by 2. Well, let's now look at how the rate of change is changing. Here it goes up by 1, and it goes up by 1, and it goes up by 1. So even though F prime is negative, it's increasing because the rate of change is getting less and less. So F prime is negative, f prime is less than 0, but it's increasing. It's you know, it's going up, I guess, on a graph, you would say. So let's see what makes sense. So it's not decreasing because, again, these are getting bigger. So it's not A, it would be B. F prime is increasing. And another way to think of this is that what's the rate of change of the rate of change, or what's F double prime? You would say like F double prime is 0, or I mean, sorry, is 1. Which basically saying is that if the second derivative is positive, then that's saying the first derivative is increasing. So the answer is B for sure. Right, 88. Let f be the function defined by f of x equals the natural log of x plus 2, or x natural log of x squared plus 1, and let g be the function defined by g of x equals x to the fifth plus x to the third. The line tangent to the graph of f at x equals 2 is parallel to the line tangent to the graph of g at x equals a, where a is a positive constant. What is the value of a? Okay, so this is actually easier than you may think. So f is this graph, f of x is this graph. And if we're talking about the line tangent to f at 2, we basically want to find f prime of 2, because that's what the tangent line is, or that's where the slope of a tangent line at that point is the derivative of the function at that point. So f prime of 2, want to find that. So let's first find what just f prime of x is in general. So using just chain rule, the derivative of the inside, 2x over x squared plus 1. So f prime of 2 would then be 2 times 2 over 4 plus 1. It'll be 4/5 then. Now let's look at g. So if you're saying that this tangent line is parallel to the tangent line of the graph of g at x equals a, then we're basically saying that this is the same slope of the tangent line as this one at x equals a. So we're basically saying that 4/5 is equal to g prime of a, because g prime of a will be the slope of the tangent line at a. So let's find what g prime of x is first. And that's simply 5x to the fourth plus 3x squared. And so then we just set this equal to 4/5, or 0.8, we could say. So 0.8 equals 5x to the fourth plus 3x squared. Let's solve this equation, yeah? So we would have 5x to the fourth plus 3x squared. All right, and let's see what we got here. Analyze graph. And it looks like about 0.447. Right, so the answer is then C. All right, just two more. 89, let f be a continuous function for all real numbers, and let g be the function defined by g of x is equal to the integral from 1 to x of f of t dt. If the average rate of change of g on the interval from 2 to 5 is 6, which of the following statements must be true? Okay, let's first define the average rate of change of g on this interval. So average rate of change of g on this This is just a slope. This is just a slope from 2 to 5. So this is just going to be then g of 5 minus g of 2 over 5 minus 2, and that's going to be equal to 6. Now let's define what g of 5 would be. G of 5 would be the integral from 1 to 5 of f of t dt. Let's set this up over here. So g of 5, so we have 6 is equal to the integral from 1 to 5 of f of t dt minus integral from 1 to 2 f t dt all over 5 minus 2, or all over 3. Let's cross multiply. So we'll get 18 is equal to this integral from 1 to 5 f of t dt minus integral from 1 to 2 f of t dt. But just using the properties of definite integrals, we're just going to take away the portion from 1 to 2. So then this will just be the integral from 2 to 5 f of t dt. And actually, I shouldn't have multiplied by 3 because that's kind of what the question is getting at. So let's keep that 3 underneath there. So let's go back. What is average value? Remember, average value. The average value of f on, remember, on some interval a, b. You remember that equation? It's just basically the average height, or average like the height of that rectangle, the area divided by the width. So it'll be, remember, 1 over b minus a times the integral from a to b of f of x dx. But then look what we got here. This our b is 5, our a is 2, and 5 minus 2 is 3. So we have that 6 is equal to 1 over 5 minus 2, the integral from 2 to 5 f of t dt. So that's what you have here. That's just another way to define that. That's exactly that's basically the definition of all that. So the answer is A. Don't overthink average value, because I know sometimes I'll have students that overthink it. It's really just, we're talking about average value of f, the output, it's the average height, the y value. Take the width divided, or take the area divided by the width. All right, last one. All right, for any function f, which of the following statements must be true? If f is defined as x equals a, then the limit as x approaches a of f of x equals f of a. Okay, so let's just make some arbitrary graph. Let's say this is a. If f is defined as x equals a, then the limit as, so okay, so it's basically saying this, that you have some function f, and so then f of a would be like over here, right? Because it would say that we want this. But the thing is that this could be an open circle. You can have an open circle here, and you could have f of a be over here. You could have that be f of a. And instead, you could just have an open circle out here. So this doesn't have to be true, because this limit could be there, but it doesn't have to be like that point. F of a could be defined up here, and vice versa. So it's not going to, a doesn't have to hold. If f is continuous at x equals a, then the limit as f of x, the limit as x goes to a of f of x equals f of a. Yeah, so here's the thing. If it's continuous at x equals a, then it has to be a closed circle because there can't be any holes or jumps. So that this wouldn't be possible. And then yeah, the limits would have to be that point. So from both sides, it would approach that point if you're coming from the negative side or positive side. So that's true. And then if f is differentiable at x equals a, then the limit as, yeah, because differentiable it has to be continuous. For something to be differentiable at that point, that means you have to have the slope of the left-hand tangent line is equal to the slope of the right-hand tangent line. Well, that wouldn't be it, but it doesn't. But in either case, if 2 holds, 3 has a hold. So then the answer then conditions 2 and 3, and so the answer then be C. All right, and there we go. We're done with the multiple choice section. So I hope that helps. Good luck.